Welcome to this video introducing our work titled Bidirectional Training for Composed Image Retrieval via Text Prompt Learning. If you're interested in the details, please scan the QR code on the right to visit our project page. The task of composed image retrieval retrieves a target image based on a user input that consists of a reference image and a modification text. The text specifies certain changes to the reference image, and the target image needs to reflect these changes while maintaining visual similarities to the reference. In many ways, it can be regarded as the retrieval version of the text-guided image editing task. Here we're showing one example from the standard Seer dataset. For this particular task, each data point contains 3 entities, as we have highlighted here. The collection of the dataset therefore requires one to first form pairs of reference and target images, which is then followed by composing the modification text that connects the two, usually through human annotators. The entire process is label-intensive and potentially expensive. For this reason, current standard datasets on this task are usually of moderate sizes. With Fashion IQ, a dataset in the fashion domain containing around 30,000 triplets of reference image, text, and target image, and Seer, a dataset with generic images consisting of approximately 36,000 such triplets. By contemporary standards, they are by no means large datasets. Considering the costly process of collecting new data, we argue that it is meaningful to study data augmentation that can help us better exploit the existing data we have. We point out that practically all current methods focus on the mapping from the reference image text pair to the target image. We call this the forward direction. But one area that is unique to this task that has yet to be explored is the reverse direction from target back to the reference. We therefore arrive at a bidirectional training scheme which can potentially double the training samples for learning. The construction of such a reverse sample involves an exchange of the reference and target images, so far straightforward. But in the meantime, one thing that is missing is the reversed text. To manually collect them is counterproductive for a data augmentation scheme. Meanwhile, we note that not all texts carry very simple semantic meanings, as the example we demonstrate here. Some are complicated, and we can't simply use handcrafted rules to replace words with adonyms. In this work, we propose to directly infer the embeddings of the reverse text through a text encoder with the absence of the actual text. To put it simple, our aim is for a text encoder to take in as input only the forward text, and produce embeddings of either direction. Here we denote the embeddings as T for the forward and T tilde for the reverse. We leverage vision and language pre-trained networks for this job. Our intuition is that such networks retain generalizable knowledge through pre-training and therefore can be fine-tuned to complete the semantic reversal of the text. We also take inspiration from work on field-shot image editing that trains the model to bind very specific visual concepts to a special text token. Here, we propose to bind the concept of query directionality to the text tokens through a text encoder fine-tuning process. We leverage a state-of-the-art 2-stage training scheme called Clip for Seer, where the first stage exactly fits our need. Following that, the second stage is the training of a model termed the combiner. At this point, we should mention that our augmentation scheme requires minimum changes to the existing pipeline and model. In fact, only some minor changes are made to the first stage, while the second stage and the combiner model is completely unchanged. Importantly, there is no change to the inference pipeline at test time. We will begin with introducing the first stage and see how we infer the embeddings of the forward and reversed text using only the forward text as input. The vanilla first stage of Clip for Seer is shown in this figure. At this stage, only the text encoder is being fine-tuned and animal-wise addition is used for multimodal fusion. The aim is to encourage the text embedding as displacement vectors between embeddings of the reference and target images. We directly input queries of both directions into the training, and in the meantime, we insert the special text tokens forward or backwards into the text, depending on if we are training on the forward or reversed queries, as distinguished by the light or dark backgrounds of the entities. When reversed, we also exchange the positions of the reference and target images. Our hope is, through fine-tuning, the text encoder will learn to capture the directions of the queries using the special tokens as hints, and produce the corresponding embeddings. Here, a seemingly minor design choice that proves to be crucial for the learning of the text reversal is to simultaneously inject the tokens for both directions. because by default, forward queries can remain intact and only the reverse queries need a special token that signifies a semantic reversal. However, we found that this harms the performance, potentially because it creates an unbalanced learning situation for the text encoder. With the text encoder fine-tuned and frozen, we progress into the second stage where the combiner module is trained. As we show here, the model is a 3-branch multimodal fusion design. As in the first stage, we train with queries of both directions at the same time. And at this stage, there's no need to distinguish whether a query is forward or reversed in the implementation front, because the model processes them in the same way. Therefore, we don't have to change anything to the training pipeline or the model. Following previous work, the model is trained with a clip-like contrastive loss. The loss for the forward queries is in its default state, where the joint embedding of the reference image and text is contrasted against the embeddings of a cluster of candidate target images. Among these candidates, one is the positive target, while others are the negatives. For the reverse queries, we formulate the sampling of the negatives, such that it is still contrasting against candidate target images, which is a detail worth mentioning. Notice the alternative in the red bounding box below. This is what we would have obtained if we simply exchanged the roles of the reference and target images. You can compare them to the forward loss on the left. The nuanced difference would result in the model sampling negatives among the cluster of reference images instead of among the candidate target images. And that will create a mismatch between the training objective and the final goal, because the model will never be asked to distinguish among reference images in inference. Our final loss is a weighted sum of the forward and the reversed losses, where the alpha is a hyperparameter that balances the weight of the two terms. The reason for balancing the terms is because we empirically discovered that the reversed loss is always much higher than the forward one, and it could harm the training. And that is likely caused by the false negatives present in the reversed queries. In essence, a one-to-one mapping in the forward path can easily become one-to-many when reversed, due to the nature of the reverse text being underspecified. Here we're showing one example where a change to a white cat is semantically reversed into a change from a white cat. Assuming the visual content is about cats, then for the reverse sample, all images with cats that are not white are valid target, but only the original reference image is labeled as such. For this exact reason, we confirm that inference on the reference queries will lead to a very low retrieval score. So we chose to inference only on the forward queries but not on the reversed. In other words, our inference strategy is identical to all existing work that do not involve bidirectional training. We empirically validated our augmentation scheme onto standard datasets, while BliffBaseer is a new competitive baseline we propose on top of ClipBaseer by replacing the clip image and text encoders with Bliff. As we have introduced, our method requires minimum changes to the training pipeline or the model, and since the reversed queries are constructed on the fly, they incur very low computational cost. A more detailed analysis of the performance can be found in our paper, with discussions on the special recall subset metric used in the SEER dataset, which is the only metric we do not outperform others using bidirectional training. At last, we show several retrieved results, where the leftmost is the reference image, and following that, from left to right, is the top 5 ranked predictions. The green bounding boxes denote the ground truth target. We demonstrate that the model is capable of reasoning over semantically complex text alongside the images. We also show that in many cases, the model can successfully retrieve on the reversed queries. Note that the text in these examples need to be interpreted in this reversed semantic. We especially point to the last example, which is a perfect illustration of how false negatives can potentially impact the inference. Notice how the top 5 retrieved results are all of non-rectangular shapes, which correspond to the text after reversal, but only one of them is labeled as positive. To conclude, in this work, we propose a bidirectional training scheme for the task of composed image retrieval, which aims at better exploiting the data we have. To obtain semantically reversed text embeddings, we leverage a pre-trained text encoder and its learnable special text tokens. Our method requires very minimum changes to the existing pipeline and incurs very small computational costs, and brings further performance increase on the new baseline that we proposed on top of a state-of-the-art method. For more details, please visit our project page on the right. Thank you for watching this video.